So the general structure that is used by most of the deep neural network models for semantic segmentation is very similar to what you're seeing at the moment on the screen, where we have a series of downsampling layers which reduce the spatial dimensionality of our input image, which is then followed by a series of upsampling layers which again increase the dimensionality of the image, such that at the very end we end up with a layer that has the same spatial dimensionality as our original input image. So if we started off with a 64 by 64 image, we end up with an output layer that is also 64 by 64 in size. So the idea behind why this works is as follows. During the downsampling portion, the model starts to gain more and more information about bigger and bigger regions of the input image. So we can use the following diagram to get a better idea and intuition about what it's doing. So for instance, if we look at this layer here and this node over here, then this node here has information about these input pixels over here. And we call this region here the context or the field of view of this node over here. So given that context there, it might cover a square region that looks something like this. Now, given that context there, it may not be enough information for us to be able to determine what is actually going on there. That could belong to a cat, it could belong to a dog, or some other furry animal. However, as we travel even further along, for instance to this layer here, and look at this node here, then this node here will be able to see what's going on in these nodes there, and these nodes in turn will be able to see what's going on in this region of the image. So that might be able to cover a square region that looks something like this. Okay, so we see that this node over here has got a much better idea about what's going on in a much larger area of the input image. And this might be enough, for us to be able to determine that there is actually a cat in the scene. So this is part of what makes deep convolutional neural networks so effective at the classification task, because as we travel even further along and we get to the very final layer, these nodes at the very end have got a much larger context and have a better view about what's going on globally in the image. However, as we start to gain more information about what's going on globally in the image, we do start to lose some spatial information. We start to lose some of the very fine-grained details about where specific things are located within the image. For the segmentation task, we wish to preserve both forms of information. We wish to preserve the information that would make a good classifier so that the model can recognize the difference between a cat, a dog, or some other thing that we want to classify. But we also want to preserve the very fine-grained details about the locations of things within the scene. So for instance, we may want to preserve information that tells us that this region over here, for instance, belongs to something that we classify as a cat. For this reason, it is quite common for segmentation models to pass some information from earlier layers directly into the upsampling layers later on in the network. So for instance, this layer here might pass information to that layer there, and this layer here might pass information to that layer there, and this one might pass information to that layer there. The specifics about what information is passed along from the earlier layers to the later layers differs quite a bit between different architectures. In some architectures, the entire output features of these earlier layers are then combined with the later layers through element-wise addition. Other architectures will pass the skip connections through a convolutional operation first before being passed on to the later layers. Now this can be useful if we wish to reduce the number of channels that are being passed along. So for instance, if this layer here contains 128 channels and we want 8 channels for this layer over here, then we can pass it through a convolutional operation that contains 8 filters. A completely different approach that is used by an architecture called SegNet is as follows. Downsampling is performed through a max pooling operation. Now this max pooling operation, we lose a certain amount of spatial information, but if we preserve the indices that are used in that max pooling operation, then that can be thought of as preserving some of that spatial information. We can then pass along those indices to some of these later layers in which we perform upsampling through through a max unpooling operation using those same indices to position the different values in the upsampled tensor. Now I'll actually go into a little bit more detail about these indices and the max unpooling operation a little later on. The purpose of the upsampling portion of the architecture is so that we end up with an output layer that has the same spatial dimensions as the original input image. So if we started off with a 320 by 320 image, then we'll have an output layer that also has 320 by 320 along the spatial dimensions. However, the number of channels might actually differ. So for instance, if we had an input image that was RGB, then the number of channels would be 3. However, the number of output channels that we would have on the very final layer is actually going to be dependent on the number of items that we wish to actually identify in the scene. So for instance, if we wish to identify 10 different types of items in the scene, we would end up with an output layer that has 10 channels in it. So given this bit of information about the fact that the number of output channels is the same as the number of items that we wish to identify, then you might start to get an aha moment. Semantic segmentation is actually just a classification task, except that we're performing, instead of just one single classification over the entire image, we're performing classification over every single pixel in the image. So we're asking ourselves, for this pixel here, what class of object does it belong to? For this pixel here, what class of object does this belong to? And so on for every single pixel in the image. The way that upsampling is performed also differs between different architectures. One very popular technique is something called a transpose convolution. Now this can be thought of as a convolutional layer that makes the spatial dimensions of the output actually larger rather than smaller when you adjust the step size. This operation is sometimes also known as a fractionally strided convolution, and it's also sometimes referred to as a deconvolution, even though it's mathematically incorrect to refer it to as a deconvolution. You will often see it being called this way. Another technique that is used for upsampling is called the max unpooling operation. In order to get an understanding for how max unpooling works, I'm going to work through an example of doing max pooling before I go through max unpooling. So let's say that we're looking at the downsampling operation that is performed at this layer over here, and let's say that the values are the values that are here in this matrix, and we're looking at little windows at a time. So we might be looking at this green window first, and we look at the maximum value, which happens to be a 7. But let's say that we want to preserve information about the index of the maximum value. So that's the 4th value in that window. So let's preserve that. We move on to the second window, this blue one here. The maximum value is 5, and the index is going to be 2. Now this orange window here, the maximum value is an 8, and the index is going to be a 1. Now this purple window here, the maximum value is going to be a 4, and the index is going to be a 2. Now, when we go and perform an upsampling through max pooling, let's say for this layer over here, we've got a set of values. Let's say that they take on these values here. We want to know where to position those values as we're upsampling. So we make use of these indices that we preserved. So we know that value 1 should be positioned in index number 4, which is over here, and all the other values in that window are going to be given a value of 0. We move on to the next one, which is going to be a 9, and we look at the indices and tells us that it should be in index 2. So it gets positioned there, and all the other values get assigned 0. The value 6 should be assigned to index 1 right there, and all the other values to 0. And this 2 value gets assigned to index 2 over here, and all the other ones get assigned to 0. So that is the max unpooling operation. One of the advantages of making use of this max unpooling operation is that it allows us to preserve some of that spatial information in a very computationally efficient way, because we're not actually adding any other learnable parameters in the process. Okay, that's it for this lesson. In the next lesson, we're going to look at the inputs, labels, and outputs that are used in a semantic segmentation network.